Anybody heard of Shannon's information theory?
Yep.
Shannon's kind of the father of information theory. And he came up with this thing called entropy. Okay, where is it? There we go. Basically, H is the symbol we usually use for entropy. X is the data. Here's the equation. Negative probability of X times the log of probability of X. Anybody seen this equation before? Well, this is the equation for entropy. And here's how we use it. Let's suppose we're trying to evaluate two divisions. I'm going to make, I know this looks just like the data I had, but I have a reason for redoing it, because I'm going to mess it up a little bit. And let's suppose we have some candidate divisions. One of them is right here, and one of them is right here. None of them are perfect, but let me ask you the question, which division is better? Which one should I choose in my decision tree? Vertical one's better, I think. But how could we measure that? I mean, you can't really sit there and eyeball your decision tree while it's building your decision tree, so how could we do that empirically? Here's the equation that's usually used with decision trees. Minus sum p log p. There. Okay, this is the Greek letter for sum. This is probability. This is the logarithm. This is log base 2 probability. Log base 2 logarithm, by the way. And that's the same probability. Here's what I'm suggesting. If we divide using the horizontal line, what is the probability that the thing on the top of it is blue? Is it not 1, 2, 3, 4, 5, 6, 6 out of 9? The answer is yes, it is 6 out of 9. And on the bottom, the probability of being blue is 1, 2, 3 out of 4, 5, 6, 7, 8. Assuming the run together points are only 1 point. Well, if we were to now sum over all the possible colors, this is a probability of blue. This is also probability of blue. And what does that mean the probability of red is? 3 out of 9 and 5 out of 8. We can calculate the entropy on this half of the division as being, we're going to sum over all the possible categories in our labels. And so we'll say it's minus 6 out of 9 times the log of 6 out of 9 plus, and now we're going to sum also over the red ones, which are 3 out of 9 times the logarithm of 3 out of 9, close parenthesis. This whole thing evaluates to the entropy on this side of the equation, on this side of the division. And we could do the same thing down here. In fact, let's just do it really fast. Minus 3 out of 8 times the log base 2 of 3 out of 8 plus 5 out of 8 times the log base 2 of 5 out of 8. Let's actually just plot it. That's going to look better. Okay, if I say minus x times the log of x divided by the log of 2 minus 1 minus x times the log of 1 minus x divided by log of 2, because the probability of red will be 1 minus the probability of x. Then it looks like this. And this is what the equation for entropy is going to look like. It's always ranging between 0 and 1. And you see how 0 indicates that you have totally blue or totally red, and 1 indicates totally blue, and both of them evaluate to low entropy. Well, 0 entropy. And in the case of 50-50 mix, this evaluates to high entropy. In the case of a decision tree, you really want low entropy among your labels, and so it turns out that Shannon entropy is a really good way to evaluate how homogeneous your labels are, and you want to reduce homogeneity. You want to increase homogeneity and reduce heterogeneity as much as possible. So what we do very often in decision trees is we pick a whole bunch of candidate divisions, and we measure the entropy of all these divisions. You can even do oblique divisions if you want to. Usually they just do axis-aligned divisions. If we measure the entropy of the labels for all of the different possible divisions that we could do, the one that reduces entropy the most is the best division. Here's a bunch of data. the root of my tree is going to be an interior node, and I could divide on this column with some value, I could divide on this column with some other value, I could divide on this column with some other value. I could try a whole bunch of candidate divisions, right? And for each one, I'm going to measure the entropy of my labels. Remember here what my labels look like. And you see how these are categorical values. Okay, so I actually have 11 different types of labels here. So the equation for entropy will sum over all 11 labels, and I'll measure the probability of each label times the log base 2 of the probability of that label. And that'll give me a number. Whichever division creates the lowest number for entropy is the best division. In other words, it creates the most homogeneity on the divisions. So if there is a case where you can get all of the heeds over here and all of the hodes over there, if there's a division that cuts them in half like that, that will be the one with the lowest entropy. In fact, that would be entropy of 0. Whereas if there's one like that, this would be a small entropy. And if you have a really bad mix of things like that, this would be high entropy. Okay, so do you see how entropy is a good way to evaluate your divisions? All right, returning to our pseudocode, when we write our pick dividing column function, in fact, we're not going to want to pick our column and then pick our pivot separately because they're kind of the same thing. So I'm going to do column and pivot together. When we do this, basically we're going to try a whole bunch of them and return the best one. And the best one is defined as the one that has the lowest entropy as measured against the labels. This is the way you would build a decision tree if your goal was to have a really good decision tree. If you have one of those 20 question balls, I guarantee you what they did is they took a whole lot of data, a whole lot of things people could think about, and they used entropy reduction to try and divide in half. Find the best questions that would divide in half. And they built a decision tree this way that ended up super balanced, looked kind of like that, and made a really nice, effective game thing. Okay, in our assignment, we're not going to use entropy reduction for a good reason. And it's not because it's hard. You guys could handle it. It's really easy. You just go code up that equation. But there's another thing, there's another way to improve decision trees called ensembles. Has anybody ever heard of an ensemble? Nobody's heard of an ensemble. Okay, I'll talk about that in a minute. There's a really easy way to pick divisions. And here's the way we're going to do it in our assignment. We're just going to say column equals ran.next feed.calls. We'll just pick a random column. Row is equal to ran.next feed.rows. And then we'll return Python style call and pivot. Okay, why are we doing it this way? This creates what's called a random tree. Now, a random tree is going to end up looking a lot more like this one. It's not going to be a great tree. Now, it's not going to be that extreme. It would be very unlikely that you'd just happen to pick one that bad, right? You're probably going to get some lucky good divisions and some unlucky good divisions in it. But as you do random divisions, you're going to get a very volatile tree, right? Meaning every time you make a tree, it's probably going to be quite a bit different from the next time you make the tree because we're making random divisions. And it turns out volatility is a really good thing in an ensemble. We're actually not going to just build a tree, we're going to build what's called a forest. And the idea of a forest is you build a whole bunch of trees and then you have them vote. And a bunch of voting trees are stronger than a single really well-constructed tree, and that's the whole intuition behind random forest. So let me draw a quick analogy there. You go to the doctor and he tells you you have a brain cloud. You're going to die. What do? Okay, if you've seen the movie, you know you get a second opinion, right? Okay, the movie, by the way, is Joe versus the Volcano, a very fine movie. If you haven't seen it, you now have a homework assignment. You go get a second opinion. Why? Because if the doctor says you have a brain cloud, well, that's a big deal. You want a second opinion. Let's suppose you go see 10 doctors, and they all tell you you have a brain cloud and you're going to die. Now what?
CV11.
Yeah, maybe you have a brain cloud. Maybe you're going to die because a whole bunch of doctors said so. In general, we tend to trust panels of doctors more than individual doctors, right? Usually. Okay, but then we find out that they were all working for the same guy who actually sold medicine for curing brain clouds, and they all were related to him, and they were all basically the same doctor, posing as different doctors. Now how do you feel about having visited this panel of doctors? Go jump into a volcano, why not? The point I'm trying to get across is this: hey, a whole bunch of opinions voting is better than one opinion, right? But the same opinion getting to vote a whole bunch of times doesn't actually strengthen the opinion. So if we built entropy reducing decision trees and then had them all vote, do you see how that's not really adding much strength? And yet counterintuitively, if we make these really bad random decision trees, which don't do super well individually, they do okay individually, just not super well. But if you have a whole bunch of them, it turns out that in an ensemble, a bunch of random trees all voting is more powerful than a bunch of smart trees all voting. And so kind of the goal in decision trees, counterintuitively, is to make trees that are kind of volatile and bad and not a little bit random, but I mean, you want them to all make good decisions, but they arrive at it in as different of a way as possible. And then when they all vote, you get a really great ensemble. So we're going to build a decision tree, and then we're going to train a whole bunch of decision trees, and then they're all going to vote together, and that's going to form an ensemble, and that's why we're going to pick the pivot and the column randomly. Now, just to add a little bit of strength to this algorithm, right here where we divide the data, where we pick, what happens if your data looks like this, and it decides to divide right there? That's bad, right? Or right there. Then it makes a leaf node, and that's really not what you want. So we want to give it a couple of tries at least. So I'm going to suggest around here, let's do for patience equals, how much patience should we have? Patience is more than 0, patience minus minus. Now it seems kind of meaningful. I'm going to select all of this code. Then in here, I'll say, if we didn't succeed at dividing, then I will break. No. If we did succeed at dividing, then I will break. You see what I'm saying here? Usually I would like this loop to not run. I'm only going to do this one time. I just want to pick a random division, and assuming that it succeeds at separating at least one point from the other points, then I'm going to say, all right, it was an acceptable division. But if that one random division didn't succeed at separating anything at all, then I'm going to say, hey, I must have really reached the leaf node. Well, if it didn't succeed at dividing anything at all, I'm going to try again. And if I tried 8 times and I still haven't been able to divide the data, then I'll say, okay, I've reached the leaf node, call it good. Okay, so I'm going to call this patience concept. I don't know if 8's a good number. You might try different numbers and see if you find one that you like. 8's probably good. But this way we'll probably divide up the data. Well, I guess that's it. I kind of wrote your decision tree for you. That stinks. I shouldn't have done that. I went too far. Let's talk about how to make an ensemble now. You still have to get it working, so there's something. How do we make an ensemble? This is my forest of decision trees. Okay? Altogether, I can call it an ensemble. Do you see that your ensemble, just like a decision tree, can also have a train method, and it can also have a predict method? How would you train your ensemble? You basically take your data and train each tree separately, and then once they're all trained, then you can say your ensemble is trained, right? Okay, how would you predict with your ensemble? Yeah, so you pass in your data, but you're going to have to pass your data into every single tree. So let's suppose this red circle for some reason represents your data. then you'll take that red circle and you run it down this tree and it'll get to the leaf node and say, okay, there's my label. And then you run it down this tree and it'll get to that leaf node and say, there's your label. And it'll run down this tree and it'll get to that leaf node and there's your label. So now you've got 3 predictions, and your predictions are hid, and who'd. What does the ensemble predict? Hid. Basically, it's the most common prediction. Or if they're continuous values, it would be the mean. Do you see how your ensemble pretty much does the same thing that baseline does? It computes the most common value for categorical values, and the mean value for continuous values